So this is a radioactive source. It's got a half-life of about 30 years, and it just produces radioactive particles. And I slide it into this is the Geiger-Müller tube, and we put it under there. And when the radioactive particles fly through here, they will trigger counts on this counter, which is attached to the Geiger-Müller tube. And so it requires, these have to be set at a certain voltage, and so it says 380 volts on top. I set it at 380 volts here. And then I can just, if I want, I can just start counting. And you can see that it counts at a very rapid rate, right? And so I'm going to stop that and reset. I'm going to pull the source out and take it far away. And what we're going to do is the first step in the procedure of the lab, which is count the background. And so we're going to set this up for 5 minutes, and I'm just going to leave it count, but you can zip through it if you want. This will, when we start counting now, so I set this for 5 minutes, which is right there. So you can probably see, maybe you can see, that that's set for 5 minutes. And so I set it there, and I tell it to count, and it'll count what's going on in this thing for 5 minutes. Notice there's no radioactive source nearby, and so it doesn't start triggering counts. But there are random events going on around us all the time, and so gradually you can see it starts to pick up pace. And so I'm going to let this run for 5 minutes, and then we'll stop. You can zoom through if you want, and just you should notice though that the counts are pretty random. Like we've been stuck on 3 for a while, right? Eventually it'll pop to 4. The rates, since they're random events, they can happen in any at any rate. And so sometimes they'll stick on a number for a long time. Sometimes you'll hit 1, 2, 3 in a row or something like that. And so we'll just watch for 5 minutes and see what happens. Okay. Yeah, right now I was just going through the procedure on it and videoing. I was going to do the intro and stuff later. I just want to get the data out so that I could work with that. Is there anything you want to do?
I don't know what I want to do, to be honest.
All right.
I was thinking I was just going to give them the information.
So this is the radioactive source, and I'm going to, it's cesium-137, a 30-year half-life. I'm going to slide it in there into the Geiger-Muller tube. I'm going to reset the counter, and this time I'm going to set the counter for 30 seconds. And so you'll see that this will trigger a high rate as we saw a few minutes ago. And so we're just going to count for 30 seconds. Whoops. Hang on a second. Stop, reset, count. There we go. Okay, so a couple things I want to note. First of all, a few minutes ago we had a 44-minute count, a 44 count of background in 5 minutes. So that if I convert that to counts per minute, that was 44 in 5 minutes. So that's 8.5 per minute, right? If it's 44 in 5 minutes, and so that's my count rate just for the background, right? So now I have 2,727 counts in 30 seconds, and so if I wanted to do a counts per minute on that, it would be twice that. And so I go to my data sheet on my lab, and I'm going to put total absorber thickness. I have no absorber thickness. There's nothing between my source and the Geiger-Muller tube, and so I put a 0 here, right? And so the count rate is twice that, because that was 30 seconds. And so in a minute, it would be 5,454. That's easy to convert into counts per minute. And the corrected count rate is this number minus that number, which hardly matters at this point. But this would be 5445. If you want, you could put 0.5 on there or something like that. And so that's my first data point. Now what we're going to do with this lab is we're going to start adding. You can see all my metal plates here, and I'm going to start adding absorbers on top of it. So we're going to have an absorber thickness here, and I'm going to write the total thickness of the absorbers, and then I'm going to put the count rates and the corrected count rates out here. And so I'm going to start by measuring the thickness of this first absorber. Whoops. And so what I get for this is about 3.1. So this is a vernier caliper, but it's got a fancy dial, and this is just millimeters, and so it's 3.1 millimeters. And so over here I'm going to write, it says centimeters, and so I'm going to write 0.31 centimeters, and then I'm going to slide it in there, right? And then I'm going to set this for 1 minute. All the rest of my counts are going to be 1 minute long. And then I'm going to start, stop, reset, count. And you can see, just by adding 1 sheet of aluminum, we've cut the count rate way down from where it was just a little bit ago when we didn't have one on there. We're getting in the thousands. So my counter stopped, and I had 407, and so I'm going to write 407 on my counter. I'm just going to round this to 9 because I don't need 4 significant figures, and so this will be 398, and that's my thickness. And now I'm going to add another sheet, and I'm getting 3.1 again for this one. Some will be different, I think. So my total thickness will be 0.62, because my first plate was 0.31 and my second plate was 0.31. And so now I'm going to put another one on top, and we're going to see what that kind of shielding does. So once again, I'll reset and count, and I'm just going to count for another minute. Just like the atmospheric effects, the decays of the radioactive nuclei in the cesium are random. And so even though we've added an absorber, we might actually get more counts during this minute than we did in the previous minute, just depending on the sort of random way in which the cesium nuclei are decaying. And so we probably won't, but it's happened before. Okay, and so it finished, and I get 333, and that means my corrected count rate is 324. Again, taking off background is sort of what we're doing each time. And now I have to measure another plate, and so I measure this plate, and I get, well, 3.1 again. And so I'm going to put another plate in there. This plate's 3.1. I'm going to reset and count for another minute. Again, each time I'm doing a minute. .332 is my count for that, 332. And so I do a corrected count rate. I'm going to stop showing you my my data sheet. You guys can sort of do that on your own. You can just follow through. You don't have to watch every video if you don't want. My next one is again 3.1, so that's another 3.1 plate. I'm going to reset and start again. So this one's 305. I have another this is 0.31 again, so another one. Reset and count again. These are all aluminum, by the way. All these little sheets are aluminum. What we're going to do next is we're going to do this top one. And then after we've done that, we're going to pull all of those out and put this block in. And then we're going to add back all these aluminum sheets one at a time again, just like we did in the first part of the procedure. So this gives me 309. I have to do a correction on that for the background, as usual. And now I put my next sheet in, which is again 3.1. Somehow I got all the same thickness. I guess it's not too surprising. So I do a reset and then a count. So in your table on the left column, you should be accumulating thickness at 0.31, 0.62, 0.93, and so on. In the next column, it's just how many counts you made in that minute. And then a third column, it's the number in the second column, minus 9 in my case, minus 9 in this case. Technically, it should be minus 8.5, but that 0.5 hardly matters. In fact, the whole 9 hardly matters compared to these numbers like 300 that we're seeing. So now on this one we got a 262. Now I'm going to take all of these guys out. Whoops, I want to keep that as stationary as I can. You don't want to move the source around too much because it changes the geometry, which can affect the count rates and stuff. And I'm going to put, oops, I forgot to measure this guy. I got to pull him back out. So I measure his thickness, right? And so you're going to pull all of those guys out. You accumulated a large thickness from those guys. And then this one is, what I get is 3.15 centimeters. Is what I get for this guy. So it's, we're going to set him on top. And so I've removed all of these guys. And so now my thickness is 3.15. And I'm going to reset and start my counter again. So now in my left-hand column, for this guy, my total thickness is 3.15. Okay, so now I got 261 on this count, and so I'm going to write that in, and I'm going to correct it. So that's, and now I'm going to take the sheet I slid in first. I've turned these upside down, and I'm going to put it in on top. it's 0.31, and so I'm going to add that to the 3.15, and that's my new total thickness. What we're doing is we're seeing how the thickness of the absorber affects the radiation count. So our count for this one was 211. I'm going to put in another sheet. It's another 0.31 centimeters. And so I'm going to slide it in there. I'm going to hit reset and count. So I get 230 for that one. Again, the absorber thickness was 0.31. I'm going to put in the next one, also 0.31 again. It was the previous one that I used. I'm going to restart it. So this is 238. Again, the thickness was 0.31. I'm going to go one more there. Terry. Oops. Oops, that's 236. So for me, I've completed my table. I had 0.31 in thickness all the way up until I had done 6 of them. and then I swapped that out for one that had 3.15 in thickness, and then I added the 0.31s back in until I had added this thing plus 1, 2, 3, 4 more. And so you should be able to get a total accumulated thickness. We read the counts off the screen, so you should be able to get those, and the corrected count is just these guys minus 9. And so now you're going to have a count rate, corrected count rate. This is this column minus the background, roughly. I subtracted 9, but you could subtract 8.5 if you wanted to. And then we're going to look at this on a graph and see how the number of counts varies with the number of thickness statistically, sort of on average. So what we want to do is graph our count rate on this chart. And so the first thing you want to do is find a scale that uses as much of the graph as possible. Right, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 ranges between the dark hash marks this way. I'll talk about the vertical scale in a second. But roughly speaking, for me, this is be 4.5 centimeters, and so I could do 0.3 centimeters roughly per hash mark, and that would get me all the way across. And so if I said I could call this 4.5 centimeters, and then 1, 2, 3, 4, 5, 3 centimeters, and 1, 2, 3, 4. Sorry, that's not 3. That's yeah, it's 3. 2, 3, 4, 5. And this would be 1.5 centimeters. So that's the thickness scale on there. And then we've got to figure out how to do the counts. The range for my counts go from a low of 202 up to 5,500, roughly speaking. And so if on a log graph, excuse me, you do these two differ by a factor of 10. So if this is like 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, this would be 200, 300, 400, 500, 600, 700, 800, 900, 1,000. That's how log scales work. And so for me, since my lowest number is 200, I'm going to call this 100 here. And this is 100, 200, 300, 400, 500, 600, 700, 800, 900, 1,000, 1,000, 2,000, 3,000. Sorry, 2,000, 3,000, 4,000. So my first number I got was about 5,400, I think. And so I might put my first number there with 0 thickness. And then my second number was about 400 with a thickness of 0.3. So this is about where I put my first data point, right? My second data point is going to go, it's at 0.31 centimeters because that was the first plate that I put in, and my count was 398. So it's going to go right about there. And then you're just going to have to graph all the rest of them, each time finding the appropriate spot, right? This would be 0.3, this would be 0.6, this would be 0.9, 1.2, and so on, right? And so you'll have to look at your chart. This would be your thickness axis, and this would be your counts axis, and you should be able to draw a line through there. So we're going to graph our data, and we want to try to graph it like this. First of all, the first count we're probably going to leave off. That was the one where we did a 30-second count and then scaled it up to a minute, where we had no aluminum on there at all. The count was very high. It was like 5,400 and something. And so on this graph, I just want you to plot the ones where you started with the 0.31 plate. And so we want a horizontal axis that goes, at least mine got up to about 4.5. You should just add up your numbers for this. This is the thickness, the cumulative thickness of your aluminum, so it's the first column, and this is the number of counts, and I'll tell you how this works in a second. So notice that their data ends at about half the graph, and that's what we want to do. So if our graph goes up to, if our data goes up to 4.5, maybe we want this thing to go up to 8 or 9 or something like that. And so if I count how many there are here, so if I count this up, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 of the dark hash marks, which means there are 30 if I can count the light ones. And so if every one of those is 0.3, does that get us up to 9 centimeters? I think it does, right? Because 0.3 times 30 is 9. And so if I leave each one of these hash marks, each one of these little hash marks as 0.3, so 0.3, 0.6, 0.9, 1.2, 1.5, 1.8, 2.1, 2.4, 2.73, and so it's 3 after 5, and so it's 9 after 15. And so that's what I would do. I would say, so this is 0.6, 0.9, 1.2, nope, that's not right. Let me try it again. This is 1.2, 2.4, 6. So, if each of the dark lines is 0.6, then that'll get me to 9 centimeters out here. And even though our data only goes up to about 4.5, we want to be able to extrapolate that in the last part of the lab. We want to have a line that we can continue because we want to see a factor of 2 drop in thickness, in counts for a given thickness. And so what you want to do is write all these numbers down and then start plotting your data points. I'll talk to you in a second about how to do the counts on the vertical axis. So here's the chart again. So the vertical axis is the y-axis scale, and these are this is a log scale. And so what you do is these are factors of 10. And so we could make this the first number 1, and this would be 2, 3, 4, 5, 6, 7, 8, 9, and this would be 10, 20, 30, 40, 50, 60, up to 100. And then if it continued, it would be going 200, 300, 400, up to 1,000. That's how log scale works. Well, we want to get our data out of here, and our data ranges from about 200 to 400, and it's sloping downward because it's decreasing as the thickness increases. So I think I would call this 10, and so I'll call this point 10 right here, and then this is 20, 30, 40, 50, 60, 70, 89. So this is 100, and so this is 200, 300, 400. Almost all of our data is in here somewhere, right? And so if we were to plot our first data point, I'll tell you what it is. It's 0.31. So 0.3 is going to be about half of 0.6. So it's somewhere here just to the right of that hash mark. And it's 398, so just below the 400. And so I would put my first data point right there, say, something like that, as best as I can do. And then my second point was 0.62, so just to the right of this guy, and 333. And so I might put it like right there. Right, those are my first 2 data points. Hopefully you can see those on the screen. And then I would plot all of those. And so they're going to be a little random noisy. And then you're going to use a ruler and just draw a best fit line through them, not connecting the dots, but just a best line. And when you do that, you'll continue it all the way to the end, right? And then what you're going to learn from that is you can pick any 2 points, like you can pick the 200, where the line crosses the 200 mark and the line crosses the 100 mark, or where the line crosses the 400 mark, which is right about here, and the line crosses the 200 mark. And the distance in thickness between those two, where there's a factor of 2 drop, like 400 to 200, or 200 to 100, or 300 to 150, and so on, the horizontal distance, the amount of thickness, will be the same for all of those. And so that's what we learned. We learned from the graph what the half thickness is, how much thickness of aluminum you need to cut the count rate in half. And then depending on how much you want to cut it down, you can add that much aluminum.